This is part one on the lesson on molecule geometry, sometimes called molecular geometry, or shapes of molecules. So we know that we have atoms that can covalently bond. So now we want to see how are they bonding? What orientation in space are those atoms going to be in? So we're going to start out with diatomic molecules. So what do we mean by diatomic molecules? Well, the prefix di means two, and atomic for atom. So these are two atom molecules. And those molecules can be elements, and there are 7 elements that exist in nature as diatomic molecules, and they are hydrogen, H2, oxygen, O2, fluorine, F2, bromine, Br2, iodine, I2, nitrogen, N2, and chlorine, Cl2. These are our Hofbrinkel elements. I have a sample of these. Under normal circumstances, the representative particle is a molecule consisting of 2 atoms covalently bonded. We can also have 2 atom molecule for compounds. So for example, hydrogen chloride has the formula HCl. So now the 2 atoms are different. And we can also have carbon monoxide, the formula CO. So let's take a look at our simplest molecule, hydrogen, H2. And we will do the Lewis structure for that. So remember, to do Lewis structures, we need to count up the valence electrons. So we have hydrogens, we have 2 of them. Each hydrogen has 1 valence electron. So we have a total of 2 valence electrons in our molecule. So we put our hydrogen symbols, and then we put in our electrons. And these 2 electrons are being shared with each other for a single bond. And we could also write that as H-H. So if we do a drawing of hydrogen, we'd have our 2 hydrogen molecules, each hydrogen having its nucleus, which is 1 proton and 1 electron in the 1s orbital in the electron cloud. And for doing geometry, we're going to see that we're going to connect the nuclei together. Because when we have instruments and we want to pinpoint where an atom is, we can't pinpoint that electron cloud, but we can see where the nucleus is. So if we connect the nucleus of one hydrogen to the nucleus of the other, we get a straight line. Of course, how else can you connect 2 points shortest distance? You need a straight line. So we call this geometry linear. So we have a linear molecule geometry, or some people say molecular geometry. Either one's fine. All right, let's look at one of our compounds. We'll look at HCl. Okay, to do the Lewis structure, we have 1 hydrogen atom in the formula and 1 chlorine atom in the formula. Our hydrogen has 1 valence electron. And our chlorine in group 17 has 7 valence electrons, for a total of 8 valence electrons. So now we write our symbols and put in our 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. So remember that hydrogen with its 1 valence electron is only going to make a single bond. So that's right there. And then chlorine, though, wants 8 electrons around it. It wants to have the octet, and we count up all the lone pair electrons and the bonding electrons around the chlorine. So 1, 2, 3, 4, 5, 6, 7, 8. So chlorine is good there. And we could also rate that as H-Cl and put in our other electrons. And if we draw that, we have our hydrogen atom with its nucleus. And then the chlorine atom is a lot bigger. Chlorine's valence electrons are in the 3rd main energy level. So we have a bigger atom. But still, when we connect one nucleus to the other nucleus, we get a straight line. We also have a linear molecule geometry. And this is true for any diatomic molecule, whether it's an element or a compound. So let's write that down. All diatomic molecules have a linear molecule geometry. There's only one way to connect 2 points, and that's with the straight line. So you don't have to do anything else. All you need to know is that if you have 2 atoms, it's linear. However, if we have 3 atoms, or 4 or 5, then we're going to have to do a little more work. So if we look at molecules with 3, 4, or 5 atoms, now we're going to use what is known as the VSEPR theory. V-S-E-P-R. VSEPR. That stands for valence, shell, electron pair, so where's repulsion, and then it's the theory. Valence shell electron pair repulsion theory. It's a very important theory in chemistry. And this says that sets of electrons around a central atom arrange themselves to be as far apart as possible. So those sets of electrons want to get as far away from each other as they can. So now, what do we mean by this sets of electrons? So electron sets can be either a single bond, a double bond, a triple bond, or a lone pair of electrons. So our single bond is one set. A double bond is one set. So that might seem kind of crazy because a single bond is 2 electrons, a double bond has 4, but they're still one set. Same with the triple bond. It is one set, and a lone pair of electrons is also one set. All right, so we're going to look at how these sets of electrons orient themselves when we have molecules. So we're going to look at the electron set geometries around the central atom, and we'll just designate that central atom with an A. So it could be different atoms, but we're just going to use A. And we're only going to be doing 3 different electron sets. So we can either have a central atom that has 2 electron sets, one that has 3 electron sets around it, or one that has 4 electron sets. There are more, but we're just going to be doing these three. All right, so when we have two electron sets, we have our central atom A, and each set, whether it's a single bond, double bond, triple bond, or a lone pair, to get as far away from each other as they can, they go on opposite sides. So we're just going to designate that the sets by a line. So our electron sets then are at a 180-degree angle. They're in a straight line. And we call this geometry of our electron set linear. Just like when we had two atoms, our electron set, when we have two sets, it's called linear. And this right here is called the electron set skeleton. This is the electron set geometry for two electron sets, and that is the skeleton. All right, so if we have an atom A, and it has three electron sets around it, to get as far away as possible, we're going to have one going up, one going off to the side, and one going off to the side. And they will be evenly spread apart. The angle here, well, if we had a full circle, it would be 360 degrees, and each section is 1/3 of a circle. So our angle here is 120 degrees. And we call this trigonal planar. It's trigonal because we have three sets, making a triangle. If we connect the edges here, we would get a triangle. And it's planar because our sets are all in the same plane. So to visualize this is our two electron sets. There's our center atom. The gray is representing the electron set. So we have two sets that they are linear. And then for three electron sets, we have our atom in the middle, and we have our three sets at 120-degree angle. Now, four electron sets, this is a little trickier because we do have 3D space, and our electrons are going to go into the 3D space to get away from each other. So we'll show you what it looks like first. So it looks like this. And we can turn this in any direction and it still ends up the same. So we have three sets, making a triangle on the bottom, and then we have one set sticking up from them. So three are below the atom, and we have one set sticking up. And if we look at the angle, this angle here, can you see that it is greater than 90 degrees? This angle is 109.5 degrees. All right, so let's see how we're going to represent that on our paper, showing the 3D aspect. So we put A, our atom, in the middle, and we're going to put one set up and one set over. So that would be like this, one set up and one set over. Now one set sticks in front and one set goes behind. And in chemistry, the way they denote that is we use what's called a wedge to show that this sticks in front of the plane of the paper, and we use a dash for our set that is behind the plane of the paper. But all these positions are exactly equal. No matter how I rotate this, it's exactly the same. So our angle here, as I mentioned, is 109.5 degrees, and we call this tetrahedral, or geometry. If we were to connect all of the endpoints for our electron sets, we would get a figure called a tetrahedron. So you might want to Google that and see what a tetrahedron looks like. It's a figure that has four faces and they're equal triangles. Tetrahedron. Okay, so this is important. Our three sets, our electron set skeletons, and our electron set geometries with their corresponding angles. So the next thing we're going to do is we're going to write down the steps to determine the geometry for any molecules that have 3, 4, or 5 atoms. Remember, if we have 2 atoms, it's linear, case closed, we don't have to worry about anything else. But if we've got 3, 4, or 5, now we have to figure it out. So step number 1 is to draw the Lewis structure. Draw the Lewis structure. Okay, and remember, to do that, we have to get the valence electron count and then put in our electrons. So we'll be doing examples in the next lesson to review how to draw Lewis structures. All right, step 2, we're going to circle the electron sets around the central atom. Circle the electron sets. Remember, a set is a single bond, a double bond, a triple bond, or a lone pair of electrons. Circle the electron sets around the central atom only. All right, after we do that, then we're going to determine the electron set geometry. And we have those 3 that we just looked at. Determine the electron set geometry. And then you're going to draw the electron set skeleton. Okay, step number 4. You're going to put the terminal, T-E-R-N, these are the end atoms, put the terminal atoms and lone pair electrons of the central atom, into the electron set skeleton. Okay, and then one more step. Step 5, we're going to connect the nuclei to determine the final geometry. And we will do examples of this in our next video.